Ciao, ciao a tutti e benvenuti su tutti i canali social di Fresca di Scienza, YouTube, Facebook, eccetera. Io sono Raffaella D'Unghia e oggi ho l'opportunità di moderare questo incontro in diretta dal titolo Come la Commissione europea si prende cura del futuro del nostro pianeta. E per chi ci segue, questo tema in realtà è vicinissimo al tema proprio del nostro progetto LEAF, con cui abbiamo organizzato la Notte Europea dei Ricercatori a Frascati e in oltre 19 città italiane. Dunque, durante questo incontro ho l'opportunità quindi avremo tutti l'opportunità di ascoltare due ricercatori eccellenti, due cosiddetti Marie Curie Fellow, quindi che hanno ricevuto anche loro finanziamenti dalla comunità europea per i loro progetti di ricerca. Dunque, per interagire anche con loro, da ora in poi parleremo in inglese. So, let's start again. Hi, everyone. I'm Raffaella Donghia from Frascati Scienza Association. And these days and today and this entire week are very, very important days for our association. And indeed, this is our Science Week that we organize within the LEAF project, where LEAF stands for Heal the Planet Future. So for this reason, I said that the project aims is very close to the researchers topics and also for the title of the direct of today. So the LEAF project has been funded by the European Commission with the call of a European Researchers' Night. The European Researchers' Night this year will be on Friday 24, but at Frasca di Scienza we decided to organize an entire week full of amazing, funny events, not just the scientifics, and dedicated to the general public. The European Researchers' Night is an occasion for Europe-wide public to get closer to researchers' project and for the European Commission to increase public awareness of the research and innovation activities. Creating an understanding of the impact of researchers' work, as we are going to listen today, and the impact of researchers' works on citizens' daily life, but also on Green Deal objectives. And it's important also to encourage young people to embark on researchers' careers. An additional and very important project for the European Commission is represented by the Marie Curie Fellowship. This project aims to fund very excellent and important research topics and researchers. And today we have a great opportunity to listen to excellent researchers, which are beneficiaries of this fellow. They are Jian Li and Maximilian Weasley. But hi guys, before to listen them, before to listen them, I'm going to introduce another person, which is the Frasca di Scienza president. Ciao Matteo.
Ciao Raffaella, and hi to everyone. I'm very honored. As Raffaella said, we already started our Science Week because, as everybody knows, the European Researchers' Night is the last Friday of September every year, in parallel in all European countries. But as Frascati Scienza, from the beginning, we decided to include our European Researchers' Night into an entire week of activity, and in particular this year we organized more than 400 events in more than 20 cities in Italy, involving more than 2,500 researchers in Italy. And I think that is a very great results that we achieved with our European Researchers' Night, because the final aim of the Researchers' Night is to make science more closer to civil society. And in this sense, when we involve such a great number of researchers, this means that we succeed in these final aims that the European Commission give to the organizer of the European Researchers' Night. Today, we have these two researchers, Maximilian Winsley and Jian Li, that I'm very glad to have here with us today, because as Raffaella already said, the aim of our project is concentrated on the European Green Deal, and both these two researchers are involved in important research that are strictly connected to environmental problem, but from the research point of view. Because when we talk about sustainability, environmental problem, what we can do, for sure, research is working. And the research founded by the European Commission is fundamental for the development of the sustainability that we every day hears from the mass media. If Raphael agree, we will start with Maximilian.
Yes.
And for what concern Maximilian work in a project that is, the name of the project is CACCI, that is an acronym that means Novel Catalyst for CO2 hydrogenation and electroreduction. Now from Maximilian we can hear what this kind of project do, but just let me say two words about this important aspect, because one of the aspects that we take care is for sure the increasing of the temperature, the worldwide temperature. And in particular, we have the production of the carbon dioxide that is one of the aspects that we follow strictly when we talk about the future of our planet. And in particular, the project in which Maximilian is involved is related to the capture of the CO2 from the atmosphere or from the exhaust of power plants into useful fuels and chemicals. Just to say, the European Commission for this project hired 14 early stage researchers from 6 universities, if I remember well. So we have a large participation of young researchers in this project, and this is exactly the aim of the European Commission that we have to follow directly. Maximilian, the floor is yours. I share your presentation.
Okay, can I start?
Sure.
Okay, so Matteo, thank you very much for the nice introduction, and I'm very happy that I have the chance to present here today. As Matteo already told you, I'm right now conducting my PhD thesis at the Paul Scherrer Institute, which is in Switzerland, close to Zurich. And the project what I'm working for is CACCI, which is a big European training network, and that is funded by the European Union. And the title of the project, as Matteo already told you, is to find a noble catalyst for CO2 hydrogenation and electroreduction. At the beginning, this title may not tell everyone too much, but just that you know, the main goal of this project is to reduce the CO2 concentration in the atmosphere. And later on, I will explain you what a catalyst and so on is. I want to start to outline the current status of carbon dioxide emissions and explain you how carbon dioxide is affecting climate change. And after I'm done with this introduction, I want to introduce you the CACCI project. I want to explain you the concept of CACCI, how they want to remove carbon dioxide from the atmosphere. Then I want to go on to explain you the structure of the network, because as Matteo already told you, there are a lot of university students involved and how we work together. And in the end, I want to give you an example, so I will explain you my role in CACCI. So where I want to start is to show you how the carbon dioxide concentration was in the atmosphere over the last 800,000 years. And we can see it here plotted with the violet line. And what we can see is that the carbon dioxide concentration was over this long period every time between 150 and 300 ppm. And in the last decade, what we can see illustrated with the blue line on the right graphic, we can see that we had an increase of the CO2 concentration inside the atmosphere over 400 ppm. And what we can see is that this increase started with the start of the industrial age, where humans started to emission a lot of CO2 inside the atmosphere. And we can see today we are already facing emissions of 35 gigatons. And what we can see, this increase in CO2 emissions is perfectly followed by the concentration of CO2 inside the atmosphere. It's just that you know the last time that the CO2 concentration was over 400 ppm inside the atmosphere is more than 3 million years ago. And back then, the global mean temperature was 2 to 3 degrees warmer. And that brings me to the next slide, where I want to explain to you why carbon dioxide can increase the global mean temperature. And this is because that carbon dioxide is a greenhouse gas. And what does this mean? All the radiation which comes from the sun to the earth is not converted to heat, but some of the radiation is reflected back from the earth's surface. And the greenhouse gas can keep this reflected radiation inside the atmosphere and can convert it to heat. So what a greenhouse gas is doing, it essentially caps the heat near the surface. And to outline it even better, I'm showing here in this slide graph, again with the red line, the CO2 concentration over the last 800,000 years. But now you can also see the temperature or the global mean temperature with the blue line. And what we can see is that when the CO2 concentration was higher, also the global mean temperature was higher. And when the CO2 concentration was lower, then also the global mean temperature was lower. And again, we can see this over the last 60 years on the right side, where we can see that the temperature increase is perfectly following the increase of the carbon dioxide concentration inside the atmosphere. And since the Industrial Revolution, the global mean temperature increased already by 1.1 degrees. And this has severe consequences for us. As we could already follow in the news, we have more frequent and severe weathers. For example, the floodings we had in Europe or the forest fires. That is, of course, accompanied by higher death rates. We have higher sea levels because the glaciers are melting faster, and also the oceans are more acidified. And of course, we have to do something against it. And on the left slide, I want to see you how the current climate policies can affect the global warming. What we can see here is the greenhouse gas emission and some prognosis for the greenhouse gas emissions. So if we, for example, want to keep the global warming well below 2 degrees, which is stated by the Paris Agreement, we have to decrease the CO2 emission by that amount. The problem is with our current policies, we can only follow the orange line, and with that, the global mean temperature would still increase by about 3 degrees, which is way too much. And this is the case because still most of our world energy production is coming from fossil fuels as coal, gas, and oil, and only 12% of the energy is produced by renewable energy sources, which means renewable energy is coming way too slow, and we are still dependent on coal, gas, and oil, where the production of energy out of these resources is accompanied by a high emission of CO2. So what we need is additional techniques, and these additional techniques are the so-called negative emission technologies. And what does this mean? These techniques are not emissioning CO2 at all, they are only removing CO2 from the atmosphere. And that's the idea behind CACHI. CACHI wants to capture carbon dioxide from the atmosphere or directly from the exhaust of power plant, and then use the excess electricity from renewable energy sources, such for example wind and solar power, to convert the CO2 to green fuels, as for example methanol, ethanol, or ethylene. And for this, we have two different routes to convert the CO2. First is the thermochemical conversion. For that, we want to use heat and hydrogen. And the second route is the electrochemical conversion, where you want to use the energy of electrons, so from the electricity, to convert CO2 to these greener fuels. But there is a problem. CO2 is a molecule with a very high activation energy. So this means to convert 1 molar of CO2, we have to bring up 1070 kilojoules. And to lower this activation energy in this project, we want to use a catalyst, because a catalyst can lower the activation energy. As you can see here, for example, this energy diagram, where you can see the reactants going to the products. And with a catalyst, we can lower the needed activation energy, for example, in this case, converting CO2 to our greener fuels. And by lowering this activation energy with the catalyst, we can speed up the conversion. So we can convert more CO2 in a shorter time period. And this is the main goal of CATCHY. We want to find the catalyst which can efficiently lower the activation energy, and thereby we can convert CO2 with a higher rate to these green fuels. And especially in CATCHY, we are focused on a special kind of catalysts, namely clusters. And these clusters are very small nanoparticles, so they're in the nano range. And the special thing about clusters is that you can already start counting the atoms. So for example, here you can see a gold cluster, which is consisting out of 923 gold atoms. So, and in the next step, I want to introduce you the structure of CATCHY. So in CATCHY, 10 beneficiaries and 2 partner organizations are included, and you can see they are distributed over whole Europe. We have, for example, partner universities, for example, the Technical University of Denmark. They are very focused on catalyst science. Then we have the Paul Scherrer Institute, where I am working. We are very focused on the characterization of those catalysts. And then we have Tier Coating Limited, which is a company, and they are very focused on the production of these cluster-based catalysts. And around these universities, research institutes, and companies, there are 14 different early stage researchers employed. We can see they are very diverse, and each of the students has its own topic. And some of this, as I told you before, we have 2 different routes, the thermochemical and the electrochemical route. And some of the students are more focused on the thermochemical conversion. And some students, as for example me, are more focused on the electrochemical conversion of CO2 to these greener fuels. And of course, I want to outline you now a little bit more what is our work. And our work is structured into 5 working packages. And with the numbers here, which are 1 to 14, you can already see where the students are involved in. And our first package is the cluster deposition. And here we want to see how we can optimize the production of the cluster, how we can be more size selective, or also if we can produce them from different metals. Or also we want to, for example, produce bimetallic clusters. We want to see if we can produce clusters which are consisting out of 2 metals, of 2 different metals, and we want to optimize all these projects. Then the working package 2 is the characterization of the deposited clusters. So we want to look at them regarding their size, also their composition, out of what elements are they consisting in the end. And furthermore, we want to also characterize their activity and selectivity for the conversion of CO2. What does this mean? For example, the activity means now how active or how much CO2 can be converted by this cluster, and the selectivity is how much CO2 can be converted to exactly one product. And then the third working package is the theoretical modeling. There we want to include some calculations, because we also want to understand how this cluster can help us by converting CO2 to these greener fuels, because in this reaction way we have some intermediates, and we want to understand how this works. And then the fourth working package is the free cluster reactivity, and there again we want to understand the mechanism behind the CO2 conversion, but in this case we don't want to use calculations. In this case we want to get this knowledge from experiments. And then the last working package 5 is where we want to use all the knowledge which we gathered from the former working package, because there we want to test the most promising catalyst or cluster, which was defined by these 4 working packages in a more industrial way, because all the testing of those first 4 working packages are on the lab scale, and in the working package 5 we want to test this catalyst in more realistic industrial conditions. And as I told you at the beginning, in the end I want to explain you what I'm doing in the CATCHY project, and I'm more focused on working package 2, and especially I am focused on the electrochemical conversion of CO2. And the first step is that I will receive the cluster-based catalyst from Tier Coating or KO11. They are very focused on producing these clusters. Here on the right side you can see a picture of a cluster gun where the clusters are deposited here on the support. And when I receive the cluster, I will test them for the activity for the electrochemical reduction of carbon dioxide, and that especially to products as formate and CO, because studies have shown these are the most economical feasible products. And then of course I will look at how the size of these clusters can affect the activity, also how the composition can affect it. For example, I will look at bimetallic clusters, so they will consist out of palladium and platinum, and I want to see how, for example, a higher palladium content can affect activity. And then of course we want to apply different potentials during that electrochemical reduction, because different potentials in the electrocatalysis means that we give different energies for the conversion of CO2. And that can also influence the activity and also, of course, cell activity. And then what I'm also going to do is to investigate the electronical and structural properties of the catalyst by using in situ X-ray absorption spectroscopy. Most of you maybe don't know what, of course, X-ray absorption spectroscopy is, but maybe the simplest analogy is that you also go to the doctor and the doctor will look at your bone structure or at your bones with X-rays. And in this case, I'm using X-rays to look at the structural properties of the catalyst. On the right side, you can see our very special cell to do this technique. You can see we have crocodile contacts to apply the potential. And through this little hole, the X-rays will go to measure it. And on the right side, you can see the electrode we're using and the clusters or the catalyst would, in this case, this black spot. But the most amazing thing about this technique is that we need a synchrotron, or also called particle accelerator, to produce this high energetic X-rays. And luckily at the Paul Scherrer Institute, we have one of the synchrotrons, and you can see this here in the picture as the ring, which has a diameter of 140 meters. And in the end, we'll select the best performing catalyst and we'll send this catalyst to Vito. And Vito is a company which is then specialized on testing this catalyst under more realistic conditions, because all my investigations will be only on the lab scale. Okay, that brings me already to the end of my presentation. I hope I could convince you of our project and make you more interested into. You can look up more about the project at our homepage, which is shown here as a link. And of course, you can also follow us at many different social networks, as LinkedIn, Facebook. You will find us under the CATCHY ETN project. Yeah. Thank you very much for your attention, and I'm ready for questions now.
Thanks, Maximilian. This is a very interesting presentation. I think that you touch a very important aspect, because first of all, we have the environmental problem and the correlation among the CO2 level and the temperature is a clear evidence of the correlation between the temperature increase.
You cannot deny.
Yeah, exactly. Because we have people that try to deny this effect. So I think that when we show clear data that demonstrate this, we cannot deny nothing. I have the first question.
Yes,
the first
sure.
question is about the time scale of the project, because the Catchy project start this year and lasts for how many years? What is the time scale of the project?
The timescale of the project is around 3.5 years. So the first half year is more the organizational stuff, and after this half a year, all the early stage researchers or PhD students should have started, and then their work is funded for 3 years by the European Union.
Okay. I don't know if Raffaella has some questions.
No, I want to thank you for this presentation.
Oh, I have another question from social network,
Yeah, sure.
Raffaella.
I can see.
Because I can see this, and the question is, which kind of material can be used as catalyst, and what is their difference? I think that this question is also related to the different type of material that can be used as catalyst. What is the difference from a chemical or physical point of view?
So type of catalyst means which elements can be used?
Which element can be used, and what is the difference among the elements?
Okay, yeah, that's a very complex question. Yeah, that's because we have, of course, we have the thermocatalysis and also the electrocatalysis, and there is a difference between those two catalysts. So in thermocatalysis, especially use copper, because they've shown that copper can convert CO2 to methanol, and methanol is a product which is very good because we can use it as a precursor in the industry. And then if we go to the electrochemical side, there are two different societies. So the one society is more focused on the copper-based catalysts, because these copper-based catalysts can perform CC coupling. So it means you can connect two CO2 molecules, and their goal is to convert CO2 to ethylene. So they are focused on copper catalysts in different structures and so on. And then there's, for example, my research. I'm focusing on platinum palladium, for example, and platinum palladium is shown that it can produce, for example, formate with a very high Faraday or high selectivity, and therefore we want to, for example, focus on platinum palladium. But yeah, every catalyst shows different product selectivity.
Yeah, a very difficult question, because it implies different type of catalyst for sure, because it depends also on the chemical mechanism that is used for the catalyst. And I have another question. This is probably from young guys that are following the event, because how is possible to participate to Marie Curie Fellow? So Maximilian, if you can tell briefly your history.
So my history is that actually you can apply online. So the positions are posted online, and you just have to find those events, and then you can apply for the position. Yeah, or there was the question how you can get to this position. But yeah, for example, I was doing already exactly this research. Yeah.
No, for example, to participate to a Marie Curie Fellow, there is a period during the year in which the European Commission propose this kind of call, because probably the people that the person that make this question is a young people interested in understanding how to apply to this kind of fellowship.
Okay, so yeah, in the end, this project is already there. So you apply then for, I was applying for the position in this project.
Okay.
Yeah.
Okay. I don't have any other questions. So, Raffaella, if you want, we can switch to Jean-Louis at this point. I don't know if Maximilian have some research duties now to be done. So if you have some other activity to do, we thanks again, Maximilian, for this great presentation and to present this important project strictly related to the aim of our European Researchers' Night. So thanks, Maximilian.
Yeah, thank you very much.
Thank you. Thank you. So let's switch to the other very excellent researcher, which is Jian Li. He is a Marie Curie Individual Fellow. from the PFL and again in Switzerland. And his research focus on the photocatalysis, again, electrocatalysis and photoelectrocatalysis for energy conversion, including water splitting, carbon dioxide reduction, nitrogen reduction. So please.
You can share your screen, Jan? Yeah.
Yeah. Okay.
Perfect.
Okay.
Jan,
so
the floor is yours.
yeah. So I'm Jenny, and I'm a Mercury Fellowship Scholar in EPFL, and I'm very happy today to deliver a talk on my research. And today I will introduce graphene-based materials for energy conversion. And we know the fossil has promoted our development of our society, but the excessive assumption of fossil fuel also leads to some problems, such as air pollution and energy crisis. Thus, it's very urgent to develop some renewable energy, such as solar energy, wind energy, ocean energy, or geothermal energy. Among these energy sources, solar energy is the most attractively renewable replacement because it's plentiful, inexhaustible, and widely distributed. And we know nature can convert solar energy and CO2 and water into sugars and oxygen. So if we can mimic this nature photosynthesis, we can also convert and store the solar energy. That is called artificial photosynthesis. It refers to any technology frameworks that can convert and store solar energy into chemicals. It can be solar water splitting or solar carbon dioxide reduction. For the artificial photosynthesis, it has two ways. One way is photocatalysis, and another way is photoelectrocatalysis. And next, we will introduce these two ways. And first, we will introduce the photocatalysis. For the photocatalysis, we need a semiconductor first. And then the semiconductor can absorb the light and then produce holes and electrons. The holes and electrons can recombine, and they also can migrate to the surface to participate in the reaction. The holes can be used for the reduction, and the electrons can be used for the reduction, and the holes can be used for oxidation. So photocatalysis has a lot of applications, such as wastewater treatment, air purification, hydrogen generation, water oxidation, CO2 reduction, and self-cleaning surface. And in this talk, we will focus on the hydrogen generation and water oxidation. And this part, I will introduce the PC cell, that is photoelectrocatalysis. For the PC cell, it usually contains 3 electrodes. The working electrode, and this is counter electrode, and it also has the reference electrode here. We don't show it. And here, this is a photoanode, and this is also a semiconductor. And when it absorbs light, it also produces electrons and holes, and the holes can migrate to the surface to participate in the water oxidation to produce oxygen, and the electrons can transfer to the counter electrode to reduce the water to produce hydrogen. And this figure is a common semiconductor. It shows the band gap and energy level. our aim is to develop efficient, stable, and low-cost photocatalysis and photoelectrocatalysis for solar energy conversion. And we know carbon materials are important materials. It was widely used in artificial photosynthesis. And carbon atoms, we know it has 3 hybridization states, sp3, sp2, and sp1. And diamond, it only contained sp3. And graphene and carbon nanotube, it only contains sp2. But is there some materials contains sp? The answer is yes, it's graphite. Graphite, it contains both sp1 and sp2 carbon atoms. So it has linear structure, free of cis-trans isomer, planar polymeric network, and uniform pores. Different connections can form different structure. We can see different connections can form different structure. And this one, there are 2 triple bonds between the 2 benzenes. It is most widely studied. We call it graphene. So next, my work will focus on this materials, graphene. And we will introduce some structure and electronic structure properties about graphene. Here we can see this graphene is a layer structure, and the layer space is 0.36 nanometer. And this is 3-dimensional structure. We can see the uniform pores distributed on these materials. And the graphene also has some excellent electronic properties, such as it has natural band gap, and it also has high carrier mobility. And so this good attributes makes graphene promising in diverse applications, such as gas separation, catalysis sensor, solar cell, and so on. And I will focus on the graphene on catalysis, especially in photocatalysis and photoelectrocatalysis. And this page, I will give an introduction about how to synthesize this graphene. Different from graphene and carbon nanotubes, they can prepare from top to up or up to bottom. But this graphene, it can only be synthesized from the bottom to up. That means you should first design the monomer, and the monomer can be reaction by the coupling reaction to synthesize this polymer. And this is some characterizations of graphene, and this Raman spectra. We can see this carbon 3 bond peak, and this is XPS. We also can see the sp1 carbons. And we also can control the morphology of the graphene. If we can tune the ligand and also tune the concentration of the monomer, we can get a different morphology. Here we can get the nanowall morphologies. So next I will give 2 works. One is the graphene for photoelectrocatalytic, and another is graphene for photocatalytic. So to show how to use graphene to design efficient photocatalytic system and PC cell. So this one I will introduce the PC cell. Here I will give another introduction about quantum dots. Quantum dots is a promising semiconductor. It has tunable band gap. It also has large surface area, so it is widely studied in artificial photosynthesis. But there is a limitation about it. That is, its electron transfer rate is much higher than its Hall's transfer rate. So if we want to improve the overall efficiency, we must improve the hole transfer rate. And we talked before, the graphene has very excellent hole mobility. So if we can combine these quantum dots and the graphene, we can improve the overall efficiency. Here, we first synthesize this graphene on this copper foil, and then we assembled the quantum dots on this graphene film, and then we assembled the PC cell to test the activity. And this is some SEM and TM image of our graphene. And we also test the PC cell activity. We can see this line is tested in dark, and we can see when we shine light on, the photocurrent increase largely. And we can also get a very good Faraday efficiency for hydrogen, and 90% Faraday efficiency for hydrogen can be obtained. And it also shows very good stability. We can see during 12 hours test, it can keep stable. So next, I will give another example for photocatalytic hydrogen evolution. Before to introduce the photocatalytic hydrogen evolution, I want to give a brief introduction about the heterojaction structure. And we know if we want to get the high efficiency, we must separate the holes and the holes and electrons. If we want to separate these holes and electrons, form the heterostructure is a promising way. But there are two types of heterojaction structure. One is type 1, another is type 2. And in this type 1, we can see all the electrons and holes are accumulated in this B, semiconductor B. So these electrons and holes will then recombine. So this is not efficiency type. So, but for type 2, we can see the electrons can transfer to the type semiconductor A, and the holes can transfer to B. So the electrons and holes can separate efficiently, and the electrons can be used for hydrogen, and the holes can be used for oxidation. So this type is a promising type. But for graphene, and we mentioned before, although it has natural band gap, but its band gap is very narrow. It's just 0.46 to 1.1 millivolt. So this narrow band gap is not very beneficial to fabricate type 2 semiconductor, because it's easy to form the type 1 heterojaction. So if we can enlarge the band gap of this semiconductor of graphene, we can fabricate the type 2 structures. So here we use the H substitution to adopt into the graphene to enlarge its band gap to form a type 2 heterostructure. And similarly, we use the bottom to up method to synthesize the H graphene. Here we design a H substituted monomer, and then we can get H substituted graphene. And this is some characterizations about the H graphene. And next, we combined this H graphene and the TiO2 to form a heterojaction. This is the characterization for the heterojaction and TM and mapping XRD and Raman. And we can see the comparison on the H graphene with TiO2. We can form a type 2 heterostructure. So they show a higher activity than this graphene and the TiO2. This TiO2 and graphene can only form the type 1 heterostructure. And we also use DFT calculation to simulate this band gap. We can see for this graphene, it only this facet can form the type 2 structure. This one it cannot form type 2 structure. But for H graphene, both of these facets can form the perfect type 2 heterojection. So that's why our activities was improved by this H-substituted graphene. And this is a schematic diagram to show why this H-graphene has better activities. You can see the electrons can transfer to this TiO2, the holes can transfer to the H-graphene, and they are separated efficiently. But for this one, you can see the electrons cannot transfer to the TiO2, so they don't have very good separation efficiency. And next, I will introduce some Marie Curie project. And my Marie Curie project is focused on the nitrogen reduction. And as we know, in industrial, the ammonia was synthesized by the Haber process, but it is proceeded under high temperature and high pressure. So if we can synthesize this ammonia at room temperature and the common temperature, it will be much. It can save a lot of energy. So electrocatalytic nitrogen reduction provide a promising way. So we can deposit our catalysts on this electrode, and then we degas this nitrogen, and the nitrogen can be reduced by the ammonia. And this side, it can occur to the oxygen evolution. So if we want to design the catalysis, the catalytic site is very important. So we should design the catalytic site. Previous study has proved that the pyridine nitrogen and the carbon-3 structure is very efficient and is a very efficient activity site for nitrogen reduction. So, but previous method cannot synthesize this site specific. So they can synthesize a lot of, you can see this is nitrogen, but not all of them nitrogen are pyridine nitrogen. Only this one are not pyridine nitrogen. So if we can control the activity site, we only synthesize this nitrogen, pyridine nitrogen. So we can largely improve the activity. So here, by using the bottom to up method, we can design different heteroatom doped graphene monomer. So such as this one is boron carbon-3 structure, and we can synthesize this boron carbon structure. We can see all this boron is a boron carbon-3 structure. And for this graphene, it's also the same. We can see all the nitrogen is pyridine or pyridine nitrogen. So we can site-specific synthesize this activity site by using a graphene's bottom-to-up method. And this can be used for the nitrogen reduction. So based on our discussion, we know graphene is a very promising materials in artificial synthesis, and it can be used for hydrogen evolution, oxygen evolution, and oxygen reduction, CO2 reduction, and nitrogen reduction. And we think I think it is a rising star in the energy conversion. Thank you for all my colleagues and my friend, and thank you Marie Curie Fellowship, and thanks this event. Thanks for your attention.
Okay, thank you. Thank you, Jean, for your presentation. First of all, would you like to tell something about your experience or some suggestion as a Marie Curie Fellow to young people which are listening to us?
For this Marie Curie Individual Fellowship, I think you should contact the host first, and then it's better if you can get some template who have get it. it's very important because there are a lot of details in red the proposal. If you missing some part, you will lost a lot of marks.
Yeah. Yanli, we have also some questions for you related to your research, because in particular, we have a couple of questions related to graphidine, because one question is how it is produced, and another, I couple these two questions, is if there are other application for graphidine, not only the one that you show in your presentation. So the two questions are related to graphidine for the material, how it is produced, what is the purity of the production, because I think that this aspect is
the purity is it's because we synthesize using this organic method, so the purity is very high. Because we will purify it after we synthesize it on this copper foil, we will use acetone and DMF to remove the residues.
Okay. Because I remember at the beginning, for example, for the research related to carbon nanotubes, during the production of the carbon nanotubes, they have not a high purity of the carbon nanotube sample. And this is one of the limitation in using, for example, nanotubes. But I remember what I studied some years ago. So probably during years, the efficiency of the production has increased for sure.
Carbon nanotubes, it can synthesize by the CVD, but now the graphene can only synthesize by solution method. And also the CVD, but can synthesize, but the structure is not so perfect if you use CVD to synthesize the graphene.
Another question, I think this is the last one. For the artificial photosynthesis, can we use other material or only the graphene?
A lot of materials, because it must be used semiconductor. So the semiconductor is a main part for the artificial photosynthesis. So we should design different semiconductor. Graphene is also a semiconductor. So we should a lot of other semiconductors such as quantum dots. And we talk here. This is also a promising semiconductor. We can tune the vacancy or the surface or the coordination of these quantum dots. We can get very different activities for different reactions, such as reduction or oxidation. We should tune the surface.
And also for you, a curiosity for myself, what is the time scale of your project?
Time scale, I just start 1 month.
So
I just started
1 month ago.
My skill
is a 3-year fellowship.
3 fellowship? Sorry?
No, 3 years fellowship.
It's 2 years fellowship.
2 years.
Yeah, but I just start 1 month. So my skill is first to synthesize these materials, and then we characterization these materials. Like you just said, we should make sure it's purity. So this characterization. And the last part, we will test the nitrogen reduction. And finally, maybe we also design some device to insert our catalysis on this device to test in practical application to see whether it can produce ammonia on the practical conditions.
For sure, we are talking about something that is research and development, but I think that this kind of research are fundamental to understand how scientific research can help in the future of our planet, right, Raffaella?
Yeah.
So I don't have other questions from social, but as I already said, this video remain on our YouTube channel. can be linked, can be reproduced also for your project. And if you have comments when you see this video, you can even write to Jean-Lee or Maximilian Winsley, that is not yet with us because he have some other scientific duties. So, Raffaella, if I think we can close the event if you are agree.
Yeah, thanks the speaker, thanks Jan again. And so congratulations for your new 2 years beginning. And thank you.
Thank you.
And stay in touch, Jean-Lee. We are. You are conducting a very interesting research, so stay in touch.
Thank you.
Thank you.